Morning, friends. This is Professor Sundar Singh from Department of Physics, Bareilly College, Bareilly. We have started a lecture series, Know Your Device. In the first part, I introduced with the PN junction diode and its variants. Now, I have decided to talk about one of the very important variant of PN junction diode, which is the light emitting diode. So it is a kind of PN junction diode which is specifically used for the purpose of emission of light. So the first question is that what is an LED or a light emitting diode? So it is nothing but a PN junction which is heavily doped for the purpose of light emission, and it is always biased under forward bias for the emission of light. The heavy doping is required so as to narrow down the depletion region and to promote the high carrier injection. Now, all the materials which are suitable for the construction of PN junction diode are not suitable for the construction of a light emitting diode. Here in the table, I have listed some of the materials which are suitable for the purpose of constructing a light emitting diode. Some of the materials are here: gallium arsenide phosphide, aluminium, gallium, indium phosphide, indium, gallium nitride, and some other materials also. I have also listed the band gaps here and the light which is emitted from these materials. The band gap of the material is basically a determining factor which color of light will be emitted when the diode is forward biased. So here you can see that gallium arsenide is basically emitting infrared light which is not visible, but some other materials, gallium arsenide phosphide, indium gallium nitride, etc., can emit light of different colors. Now the question is that why silicon and germanium are unsuitable for the construction of a light emitting diode. So here we can see that silicon and germanium, in the next slide we will see that silicon and germanium are basically indirect band gap semiconductors, and indirect band semiconductors, in case of indirect band semiconductors, most of the loss of electrons energy during the transition from conduction band to valence band is emitted as heat. Very less amount of light is emitted. So because of that, the efficiency of light emitting diode made of silicon and germanium materials will be very less, and because of that we do not prefer silicon and germanium for the construction of light emitting diodes. Here I have shown the direct band gap and indirect band gap structure of semiconductors. In this direct band gap structure, the conduction band minima, which is here shown as red point, is just lying top of the valency band maxima. So at the same k value or at the same momentum value, both conduction band minima and valence band maxima are lying. So if there is a transition of electron from the conduction band to the valency band, all the energy, all the loss of energy of the electron will be emitted as heat. So the electron changes its energy only. There is no change in the momentum or the k value of the electron. Whereas in the case of indirect band gap semiconductors, the two extrema are displaced relative to each other. So if any electron from the conduction band wants to jump into the valence band hole, then first it has to change its momentum through some collisions, which during that transition the loss of energy will be emitted as heat, and then when it has changed its momentum and equaled the momentum of a hole into which it wants to jump, then very less amount of energy of the electron will be converted into the light. So because of that, these indirect band semiconductors are not suitable for the construction of light emitting diodes. So phonon is here involved in the transition. Phonon is basically a lattice, quanta of lattice vibration, and here the total energy of the electron is converted into the light photon. So the efficiency of light emitting diodes will be higher when these devices are made of direct band semiconductors. Now this diagram shows the construction of the light emitting diode. Dome shaped diode is constructed so as to reduce the reabsorption of emitted photons inside the device. The heavily doped semiconductor PN junction is lying here. Two electrodes of the device are anode and cathode, and some other components are shown also here. Now why LEDs operate only under forward bias? So forward bias basically means the more positive of the two voltages is applied to the P region, and less positive of the two voltages applied across the junction is given to the N region. So in this case, we all know that the depletion region width lowers down, and the potential barrier height also gets reduced, and these two conditions favors the electrons and holes to cross the junction, and then they become minority charge carriers, and in the electrons recombine with the holes near the junction in the P region, mostly in the P region, and sometimes within the depletion region also. So forward bias basically favors the recombination of electrons and holes in the vicinity of the junction, and because of that forward bias is used for the emission of light in a light emitting diode. Now reverse bias cannot be used because under reverse bias the diode has a chance of getting it damaged if the voltage exceeds the reverse breakdown voltage of the diode. And secondly, the reverse bias will not allow the carriers to cross the junction, rather it will make them move away from the junction, so there will be no recombination and hence no light emission. Again, I have shown the current voltage characteristic of the PN junction diode. For different colors, we can see that this is for the infrared LED. So I think this is made of from materials like gallium arsenide, then red color LED, then orange orange color LED, and finally the blue color LED. From here, it is very much clear that as the wavelength of the emitted light is decreasing, the voltage when the diode is forward biased, so forward voltage drop across the diode is increasing with decrease in the wavelength of the emitted light. It is also clear from here, we are moving from red to blue light, and then we are seeing that the forward voltage drop across the diode is increasing. Now here we can see that how the recombination is taking place. So this is the energy band diagram of a forward bias PN junction, N-type material, and then here P-type material. This is the active region surrounding the depletion region. So electrons under forward bias, electrons are moving from N to P region, and holes are moving from P to N region. So these electrons become minority charge carriers as soon as they enter the P region, and then these minority charge carriers are lured by these electrons, these holes of the valence band. So these electrons will jump into the valence band holes and will recombine with them and producing the light. This is the principle of light emission, and the wavelength of emitted light lambda is directly dependent upon the energy band gap of the material of the light emitting diode. So if the band gap is higher, the lambda, that is the color or the wavelength of the emitted light, will be lower. So lambda is a function of energy band gap of the material. So whatever is the material band gap, it will decide the color of the emitted light. So here you can see that large band gap means higher photon energy and means shorter wavelength, and then the emission of light will be either of blue or in the ultraviolet region. But for if the material is of smaller energy band gap, then the emitted photon will have a lower energy or a longer wavelength, and the emitted light will be of red color or infrared light. Here two important factors. The working of a light emitting diode is judged in terms of internal and external quantum efficiency. Now, the internal quantum efficiency is basically the efficiency of the diode, which basically means the photons generated in the active region of the light emitting diode as per electron injected into the active region. Mathematically, it can be given as eta internal equal to rate RR upon RR plus RNR, where RR is the radiative recombination rate, RNR is the non-radiative recombination rate. So radiative recombinations are those in which the loss of electron energy is converted into the emission of photon, that is the radiation, photon radiation is occurring there, whereas some of the transitions may not result into the emission of photon. So those recombinations are known as non-radiative recombinations. So internal quantum efficiency can be maximum 1 or it can be 100%, whereas the actual efficiency of a diode is basically measured in terms of the external quantum efficiency, which is basically the number of photons emitted to free space, that is the number of photons which are coming out of the device per electron injected into the active region of the diode. So this is the actual efficiency of the light emitting diode. Now this eta external can be written as eta internal times the eta extraction. This eta extraction is basically the efficiency of extraction of photons out of the device. Now this eta external, that is the external quantum efficiency, is always less than or equal to the internal quantum efficiency of the light emitting diode. Here I have made a comparison between these two type of frequencies of light emitting diode. Now internal quantum efficiency basically considers photons generated inside the device, whereas external quantum efficiency considers the photons that are coming out of the device. Now this internal quantum efficiency depends on the radiative as well as non-radiative recombinations, whereas the external quantum efficiency depends on internal quantum efficiency as well as on the efficiency of light extraction from the device. Internal quantum efficiency is higher, whereas external quantum efficiency is always less than or can be maximum equal to the internal quantum efficiency. Here are some of the effects of injection current, the forward current that is we are injecting into the device, and what are the effects of that injection current. So if current is increasing, then more number of electrons and holes are crossing the junction, so that will result into the more recombinations and hence more photons will be emitted. So as a result, light intensity will increase approximately in proportional to the current over the normal operating range. But if we increase the forward injection current to a high level, then we will see that there will be a drop in the efficiency of the light emitting diode because of the factors of either due to the overflow of carriers in the active region causing lowering down the recombination of electrons and holes, or because of the non-radiative other recombinations, heat will be produced in the device. So very high injection currents will not lead to the increase in the efficiency of the device, rather these will create a drop in the efficiency of the device. So to limit the this injection current, normally limiting resistor is used in series with the light emitting diode, so that excessive current do not flow through the device and there is no loss in the efficiency of the device. Here are some of the advantages and applications of the device. You can see that LED is a highly efficient device. It has a fast switching times, 2.5 nanosecond to 15 nanosecond. So the device switches on off very fast. It has a very small size, so it can be packed as a small device. It has a long life, 50,000 to 1 lakh hours, and low power consumption. Device consumes very low power, and the consumption is of the order of few milliwatts. Because it do not uses mercury, so it is environment friendly. Also, there are no toxic materials used in the construction of this device. Some of the applications you may come across in your daily life are indicator lamps, traffic signals, LCD backlighting, remote controls. Infrared LEDs are used in the remote controls that we are using in our daily life. Digital displays, automotive lighting, optical fiber communication, and general and medical lighting. So you can see that in every walk of life you can find some one or some other LED being used. Finally, I have listed some important problems involving light emitting diode. In the first problem, I have used LED as a with the current limiting resistor. Three different color LEDs are connected in series with a limiting resistor and a power supply. So you have to solve some, you have to calculate some of the parameters for this combination. Some other problems are also here just to check your knowledge, and these are important problems. If you solve these problems, you will get a real feeling of what actually is a light emitting diode. So thank you, friends. This was the second lecture of the Know Your Device lecture series. Hopefully, I think you would have enjoyed the first lecture also, and this one is for uh, second lecture. Now, in the next lecture, probably we will discuss about the some other device. I think it should be transistor, bipolar junction transistors. So till then, bye bye. Thank you.